All right, Andy, I'm going to do a little analysis of these struts and kind of go super nerdy on the reason why the vehicle moves sideways and just some considerations. So this is the best picture I could find that you sent me that depicted the vehicle on its side and where the struts were located. I'm only going to focus on the horizontal movement of the vehicle. But another thing I've noticed in this picture are those ratchet straps. They're basically on the same plane as the strut, which means that the strut is just immediately fighting those ratchet straps. Normally the ratchet would be opposing the horizontal force we'll talk about in a minute, but in this setup it's not doing that so much. So the blue line that you see here is depicting the strut force. So if you started to pump the hydrofusion, that blue line is representing the force vector that's created by the strut as it gets extended, as it gets pressurized. The green arrow represents the vertical component of that force, and it's what would be wanting to make the vehicle lift, which was the ultimate goal in the rescue. The red arrow is a force vector component of the strut force that is being applied horizontally. There was only a picture of the vehicle from its side, so maybe to see this a little bit better, we're going to kind of reconfigure and look from the front of the vehicle and draw what's called a free body diagram. So here you can see we've got the truck. I'll just Google search truck F350s. Guesstimate it weighs around 7,000 pounds. And I just had to make some other assumptions, so I assumed that the strut was at 20 degrees from the ground, 70 degrees at the vehicle, which is a very, very steep angle. And when you draw those force vector components of the strut force in, you can see the V is the vertical, that green arrow. The horizontal is the red arrow, and when you draw them out like that, you can comparatively look at the lengths of those, and the lengths are the magnitudes, and the magnitude could be a measurement in like inches, or it could be a measurement of weight or force. And so just immediately you can tell that the horizontal component of that strut force is considerably more than the vertical component. So immediately your spidey senses should be sticking up. So to understand everything at play, I say everything, a few things in particular that we're going to mine into. First will be the effects of friction. So if we took all the struts away and we were just to tie a rope onto the truck and say, let's drag it sideways, what would it take to do that? Well, you've got to overcome the friction between the truck and the ground. You can look up all sorts of different friction coefficients on the internet and reference sources. Finding metal on dirt's a little bit difficult, but when you start kind of looking into it, a lot of them are 0.4, 0.6, 0.5. So another assumption that I'm making is that the friction coefficient between the vehicle and the ground was a 0.5 friction coefficient. And mathematically speaking, that's typically called mu. The force required to move the truck is mu, or the friction coefficient, times the weight. And so if we have the 0.5 is our friction coefficient times 7,000 pounds is our weight, then the force required to move the truck sideways is 3,500 pounds. So if we think of that, looking at it from this perspective, you can see that, back up. So it would take 3,500 pounds to move the truck sideways. So let's now zero in on the green arrow, the vertical component of the strut force. And so that's the amount of force that you need to be able to lift the truck in the air. And so as you can tell, we're lifting the left side of the truck. And as we did that, the right side of the truck would probably stay on the ground or be on cribbing or something like that. And so in this instant, it's one of the rare occasions where we are actually lifting about half of the load. And so one half of the load is on the left on the ground, the other half is, or correction, on the right on the ground, the other half is on the left being lifted vertically by the strut. So if our truck weighs 7,000 pounds, half of that is 3,500. So it requires 3,500 pounds of vertical force to lift the truck. So not knowing, not even worrying about how much force was actually generated by the strut, we know that in order to lift the truck, we have to have 3,500 pounds of vertical lifting force. And so if you use that 3,500 pounds and said, okay, the length of that green arrow represents 3,500 pounds, and you compare that to H or S, the horizontal force of the strut, you can then determine just by comparing the lengths of them what the force is in those different components. And so just looking at it, you can tell that H is about 3 times what V is. So again, just saying it here. So H is just about 3 times of what V is. And H represents that horizontal component of the force that's being generated as we pump the strut up. So, and the almost 3 times is that precisely would be 9,615 pounds would be that force that would be being applied horizontally. So to prove that, to prove those numbers, I ran the math on it. So if the vertical component is 3,500, then you could run the math to figure out the horizontal component, 9,600, and or how much force would have to be in your strut in order for it to be able to lift 3,500 pounds. In this case, it's 10,000 pounds. So your strut would have to lift 10,000 pounds. So if we look at it from this perspective, okay, well, that means that I can now see all the values that are being applied everywhere to get the vehicle to move upwards. Well, if that's the case, then it requires 9,615 pounds of horizontal force moving from left to right. Something has to resist that. Well, most of the time when you have a strut very vertically, what resists that is the friction between the object and the ground, and oftentimes it's also aided by that ratchet strap, and that ratchet strap would have to resist that horizontal component. And so even if you are able to get your ratchets down low on the vehicle in this particular circumstance, you would be exceeding the ratings of your ratchet straps. But nonetheless, in the instance that you had, you're pushing the truck from left to right with 9,600 pounds of force, and that has to be resisted by something. Well, friction is only resisting that force by 3,500 pounds, which means that other 6,000 or so has got to be opposed by something. And real commonly, and you said it on the phone, you drive pickets in the ground, you pin it to the ground, something like that. So if we were to move the vehicle out of our free body diagram and only look at the vectors involved, you can kind of easily see now that you have 3,500 pounds in the pink coming from right to left. You have 9,600 pounds coming from left to right in the red, and so those don't cancel each other out. There's an extra 6,100 pounds of force that has to be opposed by something. And you mentioned that the vehicle slid a little bit. Well, it makes sense that it slid because there wasn't something resisting that other 6,000 pounds of horizontal force that was being generated. So hopefully this is kind of helpful to think about struts and angles and horizontal components, vertical components, how they play with each other. And for me, it helps me remember and identify the importance of when you're lifting your strut needing to be vertical, more vertical. And we're always talking about that 30 to 60 degree lifting angle, and in recent big rig classes they've even been teaching to have them completely upright. Well, if they're completely upright, cool, but something has to resist the tipping, the horizontal component of the truck or object wanting to tip left and right. And so you've got to put something in to resist that. And so of late, they've been doing lateral ties with grip hoists and all sorts of things. You could also do that with other struts. But hopefully it's a little helpful, probably a little overboard, but I had a good time making it. So be well. Catch you later.